when you prove a Euclidean geometry theorem, whether it's your grade 11 Euclidean geometry theorems or whether it's these grade 12 Euclidean geometry theorems, you have to remember they always have the following format. The format is given. Good news to you guys, you don't have to memorize the given. The given is normally part of the diagram. It's already there. So what has been given? What's been given is DE parallel to BC in triangle ABC. That normally, they give you the diagram and they write that given part down. However, the RTP, which is the required to prove, and the construction, that is hardly ever given to you guys. You have to memorize that. This is where the theorem proof starts. And I did tell the grade 11 teachers last year when they were doing the theorem proofs with you to make sure you understand the format of a Euclidean geometry theorem proof, because the IB requires you to know to write RTP, required to prove. They even sometimes they leave like a RTP with a line there for you to fill in. I remember we did give you those ones last year so you can see. And then construction, we have to do the construction. Okay, so what's required to prove here? What is required to prove is simply this. I need to prove that AD over DB is equal to AE over EC. I need to prove the theorem. Okay, so I'm required to prove AD over DB is equal to AE over EC. Now, all theorems start with a construction. If you do not memorize the construction, you can literally just leave a blank, because if you don't do the correct construction, everything from here on is what we call a breakdown. It's wrong. This construction is quite interesting. The construction says, draw heights H and K on sides AD and AE. So you go to side AD, and on side AD you draw a height there. So it's got to be 90 degrees, and you call that height H. Then you go to the opposite side, so AE, and you draw a 90-degree height over there. And you can call that height K. So you draw a height H perpendicular to side AD. You label it H. And you draw a height K perpendicular to AE, and you label it K. And then you also join up these lines, these diagonals. And we are going to prove this theorem by using areas of triangles. That's why we had, right at the beginning, we had that whole discussion about the area of a triangle. Got it? So I'm going to go and I'm going to say the following. The area of triangle ADE over the area of triangle, and this one is going to be, I always forget, so I just need to confirm, DBE or BDE, it really doesn't matter. Okay, now if I look at triangle ADE at the top there, it's half base times perpendicular height. Do you agree? What's my base for that triangle? It's AD. What's my height for that triangle? H. I put it on there. I constructed the height. I called it H. Now let's look at triangle BDE here at the bottom. The base for that triangle, do you guys agree, is BD or DB? What is the height for that triangle? H. Can you see that? I'll turn it sideways so you can see it. Look. This triangle right there, the base is over here. Where's the height? The height is exterior to the triangle. It's outside. Because this is an obtuse angle triangle. Can you see that? So because this is an obtuse angle triangle, the height for that triangle is also equal to H. So I can simplify that. Do you guys agree? That simplifies to what? AD over DB. Now we're going to do exactly the same thing. But I'm going to, yep. The height again. Do you want to see the height thing again? Okay, so if I turn it sideways over here, here's my first triangle that I was looking at. Okay, so for this particular triangle, I know AD is my base, there's my base, and I know my height, there's H. Now if I look at this triangle over here, this triangle over here has got an obtuse angle. And look, it's got a common vertex of E. So this is back to the fact that those two triangles have a common vertex of E, so they've got a common height of H. Can you see that? They've got that common height. So I do exactly the same thing, but I do it on the other side of the triangle. So now I'm going to say, I'm again going to look at the triangle ADE, and I'm going to look at the area of triangle CDE at the bottom here. Now, I agree I'm working with the exact same triangle, but I'm now going to work with a different base. So in the first part, I worked with AD as the base. Now I'm going to work with AE as the base. Can you see that? So if AE is the base, what will be the height of that triangle? K. Then I look at that bottom triangle, that triangle CDE. What's going to be the base of that triangle? EC or CE. And just like the previous one, if I turn it sideways, you can see this triangle, the base there is AE, the height is there at K. This triangle has got that common vertex D. So because it's got that common vertex D, it's got the common height of K, but its base is EC. And if I simplify that, what do I get? But what can you tell me about the area of triangle BDE and the area of triangle CDE? That's again one of the stuff that we discussed right at the beginning. What can you tell me about the area of triangle DBE and triangle CDE? They're equal because they've got the same base, DE, and the same height, because they're between the parallel lines. So that means area of triangle BDE is equal to the area of triangle CDE, and the reason is going to be same base and height. So, if those two are exactly the same triangle, and those two triangles have equal areas, what's my final deduction then? Come on, it's right there in front of your face. What am I required to prove? This is equal to that. And of course they're equal to each other, because this area is equal to that area because it's the same triangle. It's both triangle ADE. And I've just said this area is equal to that area, so therefore, finally, AD over DB is equal to AE over EC. And I've proven what I was required to prove, so I'm done, finished. Not too bad. In all honesty, I still hell of a lot easier than the midpoint theorem that you guys were required to prove in grade 10. Okay, so yes, it's tricky because there's a lot of brand new stuff, but we did discuss all of the little bits and pieces earlier, and because we discussed all of the little bits and pieces earlier, we just had to put all of it together to do the theorem proof. So this is one of the theorems that is in your syllabus, meaning they can ask it. They've never asked it before, but they can definitely ask it, so you have to be aware of that. What I will do for you guys is I will do a summary of all the theorems, pretty much grade 8, 9, 10, 11, and 12, all of them at the end. And I'll also do a summary of all the theorems that you are required to prove. So you will have two documents, the one stating everything, even vertically opposite angles, even alternate angles. You'll have a document like that one, and then you'll have a second document that shows you all of the different theorems and the proof of those different theorems. And I'll even try and find examples in past papers of how they've asked it. Okay, so I'll do it like this is the way they asked it in the 2016 paper, this is how you answer it, just so you know exactly which ones you need to know. Okay, pleasure. Okay, that will only come at the end of the Euclidean geometry section. Espen will nag me for it, so don't worry, it will happen. No, Espen is perfect. I always tell people, I've got a list of stuff to do. It's on my to-do list. It just depends on how high up the priority it is. So the more you nag me, the higher up it moves up the priority scale. So, like I said, this is why nagging, like Espen does, is a really good thing. Okay. Amy has also nagged me a couple of times, I know. It works though, you're right. Yeah, it works. Okay, so, that is then the theory that I wanted to discuss with you guys. And since we have some more time, we're going to continue with this. So go to page 7, keep practicing.